This is a Taig Micro Lathe, and I have been absolutely tickled with it. I mean, this lathe does not owe me a thing. That being said, the major weak point of these lathes is the stock spindle. So let's talk about that. This is the original spindle from my Taig lathe. This is one of two spindles like this that they offer. This one is the 3/4 16 version, which refers to the thread on the end of the spindle nose here for attaching your chucks. So that's a 3/4 inch by 16 TPI thread, in case anybody's in Europe and you're not familiar. It's also got a taper in there that will accept some proprietary collets from Taig. In practice, I have literally never used that for two reasons. One, I would have had to buy proprietary collets, which are useless outside of this lathe. And two, this spindle's not actually hardened. I believe this is 12L14, which is pretty darn soft. They use a sealed ball bearing in the front and you can just kind of see in there, a shielded ball bearing in the back. So it doesn't have any contacting seals that I'm aware of. I can only assume that this is a non-contacting seal based on the level of friction or lack thereof with rotating this thing. And they've actually got a pretty traditional cartridge style design where they've got a spacer and you tighten down this rear preload nut against the spacer, and that's what controls the preload of the bearings. Now in practice I've never done that because it showed up from the factory preloaded and ready to go. But let's talk about the big weak point of this spindle. Man, this spindle bore's filthy. Let's try that again. Let's talk about the big weak point of this spindle. It's that bore right there. That is about 5/16 of an inch, which is tiny. Just for size comparison, here is one of the chucks that I typically use with this little lathe. This is a lovely little chuck made by Shoreline. Works just like every other self-centering 3-jaw in the world. But as you can see, even with that, which is a relatively large opening, most of that gets sort of closed down and eaten by the spindle taper. So pretty pathetic spindle bore. It really limits your ability to hold long stock, and you end up spending a lot of time at the bandsaw or at the hacksaw cutting off a section of stock to a couple inches or something so you can grab it. Now, it is worth mentioning that Taig actually makes an ecosystem around the ER16 collet system. So this is actually an ER16 adapter for this spindle, which you can buy from Taig. There's two problems with this. One, the runout's not that great on this collet adapter. It's under a couple thousandths, but like a good collet spindle can get you under 1/2 thousandth of runout, and this is nowhere near that. And two is it's a ton of stick out. You can see even when it's tightened down, that's a lot of wasted space. Now, the best remedy for this is to just use the ER16 spindle that Taig sells. You can buy this spindle with a hardened ER16 nose. If you're buying a new Taig lathe, buy that. Don't buy this. But I didn't know any better at the time. I actually have that spindle on my mill, but by the time I bought that, I had already invested in a bunch of the 3/4 16 tooling that fits the spindle nose. I had chucks and everything. So, let's talk about the solution. The solution turned out to be to make my own spindle, which takes ER32 collets. This is an ER32 collet block that I use in the mill, but I'm just going to use it as an example of the ER32 spindle design. So it's got a taper in here. I believe the critical angle from center line to taper is 8 degrees. I should know that, since I just ground one. And it's got this weird looking collet nut, which you use a hook spanner on. And it's got this eccentric feature in it, which is not a defect. It allows the collet to snap in to the spindle nose. So this is holding itself together now. So when you want to use these, you have to, before you put it on the stock, you have to snap the collet into the spindle, which I can't seem to get out now. You have to snap the collet into the spindle nut, then you slide this over the stock, and then you can put kind of that whole assembly in your spindle, or I guess you could slide the stock in afterward. As you tighten this down, the taper engages and forces that nut to close down, or forces the collet to close down. I like this collet system over 5C because I have a very small shop, don't have a lot of space, and a complete set of ER32 collets is about that big right there. So not a lot of space at all to go that whole range, because these collets have a relatively wide clamping range. So this is why I lean towards ER, is because I can cover a lot of ground with a very small number of collets. So that's why I went with ER32. You can buy a 5C spindle from Taig. It's about $600. After having built my own spindle, I can say that's a fair price, but I didn't want a 5C spindle, I wanted an ER32 spindle. And I initially would not have thought to make one myself, and then these came along. These are Nachi brand angular contact bearings, and these are actually meant for supporting very large ball screws, like the ends of ball screw lead screws that are used in large machine tools and automation equipment and things. But fundamentally, they are angular contact ball bearings. But that's essentially like a cross between a plain ball bearing and a tapered roller bearing. These happen to be not sealed. According to Nachi's documentation, they can be oil or grease lubricated. I've opted to lubricate them with grease because it's a whole lot simpler than designing an oil lubrication system, and I'm not even a real mechanical engineer. So there's that. But I got access to about somewhere between 4 and 6 of these from my university's I don't think we need this anymore bin. I have no idea where they came from. I can only assume they came out of some kind of automation equipment or some kind of research apparatus with a ball screw in it that got scrapped. But I got a hold of some of these, and I started thinking, well, wait a minute. You know, a pair of these is about probably a $200 or $300 set of bearings. They're pretty oversized for this lathe spindle. Actually, it looks like I could fit the outside of the I could fit the entire original spindle bearings through the bore of these bearings. They're hilariously oversized. But I could use a pair of them, one at each end of the spindle, much like they've done with this. One at the front, one at the back, and a preload nut to squish them together, and I could make a spindle. So I started looking at this. At the time, I didn't know anything about spindle design, or really, I didn't know much about bearings in general. I had changed the wheel bearings on my truck, but that was about all I knew. So let's talk about the constraints that I put on myself early on, some of which stuck, some of which didn't. Number one was I wanted to avoid grinding. Ominous foreshadowing. Like I said, I've got access to a machine shop through my university, and that included a manual lathe of pretty substantial size and a couple of Bridgeport mills. What it did not include was grinding equipment. No surface grinder, no cylindrical grinder, nothing like that. We had a homemade tool post grinder made out of an old CNC router spindle for the lathe, and it worked well, but it's very cumbersome to use, and of course it's not great for the lathe to get grinding dust anywhere near it, so I was trying to avoid doing that. I also was thoroughly uncomfortable using grinding equipment. I wasn't experienced with it, so I was trying to dodge grinding. That didn't work. I'll talk about why and what I ended up doing later, but that was an original objective, was no grinding. Second objective, which actually did work, was no heat treating. that was kind of an interesting one because I knew from my experience with this spindle, and there are a couple of spots where I had actually galled the spindle taper a little bit. I knew that I didn't want a soft spindle again. 10 times out of 10, you would rather your tooling or your work holding or whatever wear and your spindle taper not wear. I wanted a hard spindle. But since we had no access to grinding equipment, and we certainly didn't have access to professional heat treating equipment, and even if we did, I wouldn't have known how to use it, I didn't want to get in the business of heat treating. So the way I was going to manage that is to compromise and use semi-hard stock. If you don't know, you can get 4140 semi-hard from McMaster-Carr, and I think you can probably get it from Asumi and maybe Online Metals, you know, the usual suspects. McMaster claims that this is Rockwell C25. Rockwell C25 hardness. I don't have access to a hardness tester, so we're going to take McMaster at their word. I bought about a foot of this stuff. It was relatively inexpensive, and I used carbide on the 14-inch University lathe to machine this. And actually, I used a couple of high-speed steel drills to get the bulk of the material out for the spindle bore. So it is hard, but it's not so hard that you can't machine it, especially with carbide. So that was objective 2. Objective 3 is I wanted it sealed. Now, what do I mean by that? This front bearing is a sealed bearing. This rear bearing, however, is only shielded. So what that means is there's just kind of a cover plate, and very particularly determined crud can still get into the bearing through the gaps in the cover. Now, I use emery paper on the lathe. Sometimes I use a little bit of like carburetor cleaner or other solvents to clean parts. I do some kind of harsh stuff on the lathe, not to mention the tiny bits of metal flying off of it. There's lots of contaminants that could get into bearings. That didn't matter to me a whole lot with maybe a $40, $50 set of bearings, if even that, on the stock spindle. But a pair of these is worth some money. And I knew that going into this, that the only way this made any sense is if I designed it well enough that hopefully I never had to change the bearings. So I wanted it to be sealed. Now, initially, I thought that I could do this with just grease seals off of McMaster-Carr. I actually made a handful of 3D printed bearing covers which accept a grease seal. This actually worked well from a sealing perspective, but it generated way too much friction. The spindle would have been difficult to turn with your hand, which was just annoying to use, especially if you're trying to take measurements on a part. And under normal operating speed, it actually generated enough friction with the shaft for quite a bit of temperature rise, like 15 or 20 degrees. Not enough to hurt the bearings, but enough to irritate me into coming up with another option because I didn't want the temperature swings on the bearings and on my parts. So I had to adjust course on this, and I went with Labyrinth seals. So this is a non-contacting type of seal. I actually had to make these myself. It was a lot of work. Ideally, if you're building a spindle like this, you would just buy sealed bearings, which include generally, I think, some type of Labyrinth seal. But again, these bearings were free, so I was trying to work around the free stuff that I had. Then the last constraint that I had is I wanted to support magnetic bases. Now, most of you, if you're watching this video, probably know exactly what I'm talking about, but if you don't, this is a mag base. This is a little baby one, actually. This is a switchable magnet, and this is an articulating indicator arm. When you tighten this knob up, the arm becomes very, very rigid. So if you have magnetic machine tools, which generally they are, most larger machine tools are made of cast iron, then you can stick one of these to the table of your mill, or to the bed of your lathe, or the carriage of the lathe, or the tailstock, or any number of different places, and you can put your indicator wherever you need it. and it's awesome. One of the very unfortunate compromises with Taig machine tools is that to keep them light and to cut costs, because aluminum is so much easier to machine, their spindle is aluminum. Good luck fastening a mag base onto that. So I wanted, with this new spindle, to have some way of attaching magnetic fixturing. Obviously, no grinding was an abject failure for a lot of reasons, mostly on the diameter that actually mates with the bearings. I figured out pretty quickly that I wasn't going to be able to get a consistent enough diameter or a good enough finish without grinding. Probably could have got a good enough finish with some kind of polishing, like with some sandpaper or something, but getting a really, really consistent round diameter was going to be extremely difficult without grinding. So ended up just using the tool post grinder on the lathe. I had to come up with a lot of fixturing to do the taper grinding. Normally you would grind a spindle taper like this in place, running on its own bearings on the lathe that the spindle is going on. In this instance, I couldn't really do that because you can't put a tool post grinder on the Taig lathe, at least not to grind a taper, because the compound available from Taig, it's nowhere near accurate enough. So I ended up creating this fixture so that I could use the tool post grinder on a 14-inch lathe at my university and drive the spindle with a stepper motor and grind it in place that way. So I'll take a second and walk through how that works. So this was actually a 4-jaw chuck, but it was the only thing that we had that was similar to a faceplate. So I just took the jaws out, and I'm using the T-slots in the chuck as T-slots on a faceplate. And then I've got some 1, 2, 3 blocks to create some clearance for a spindle pulley. And then I've got this piece of 1/2-inch plate, which I had laser cut actually. That was a really nice time saver. I mounted that on the lathe using socket head cap screws and T-nuts in the T-slots. And once I had this on the lathe, I turned the lathe on and faced this surface. So then that entire surface was guaranteed to be true to the lathe. So once I had that done, I positioned the spindle in the center of the fixture, and I put a 3D printed timing pulley on the back of the spindle. And then I bolted on this little motor mount for a NEMA 23 motor, which was also laser cut. And it rides in these slots, which allow you to tension the timing belt. So I bolted on the spindle, and I bolted on this motor mount, put the timing belt on. There's no pulley in the CAD model, but there was a timing pulley here, and tightened up the belt, and I connected a constant speed stepper motor controller, which is what this little rectangular cutout is for. It just gave that a place to mount, and I powered that with a 24-volt power supply. So what that allowed me to do was use the stepper motor to turn this spindle at pretty much whatever speed I wanted. And interesting sidebar, it was actually non-trivial to get the spindle of the big lathe not to move at all. You can see I had it in the lowest gear, which makes it much more resistant to movement, but it'll still move. I had actually clamps on the foot brake, because this lathe has a foot brake, but there was still just a little bit of movement possible because this is a geared headstock and there's always a little bit of slop in the gears. So to preload all the gears so that it wouldn't move, I put the chuck key into the cam lock fasteners on the spindle and hung some scrap off of it to act as weight to preload it. And it didn't have to be a lot of weight, just enough to keep it from being able to kind of vibrate between both sides of the gear teeth in the headstock. It looked completely ridiculous, but it actually worked really well. Yeah, I actually ground this spindle twice. And when I say ground, I mean I did the final grind on the taper of the spindle and the spindle nose in place running on these bearings. I had to do that twice, which was not by choice. The first time I did it, I had actually not checked the parallelism, or excuse me, the perpendicularity of the face of this lock nut. And I just assumed that it was good enough, which was foolish looking back. But I tightened it down, and I ground the spindle, and it ran basically perfectly true, under a 10,000th of runout. And then I took the preload nut off to put the seals on, because I had taken one of the seals off to put it in the grinding fixture. Terrible idea, because what was actually happening there was the spindle shaft was getting forced into a banana shape by the inaccurate preload nut. And so I forced it into a banana shape, I ground it while it was in its banana state, and then I took the preload nut off, and of course there's no way I could have gotten it back into exactly that same banana shape. I couldn't have distorted it exactly that same amount. Again, there's no chance that's going to happen. So when I went to put the preload nut back on, no matter what I did, I couldn't get the spindle to run true. I mean, it was a couple thousandths out, where originally after it was ground, it was under a 10,000th of runout. So I scratched my head for a long time on that, and I thought, well, maybe the bearings are bad, maybe I designed something wrong. Finally narrowed it down to that nut, which I was able to fix on the mill, thankfully, and then had to go back and regrind the entire spindle. So put it back on the lathe, set up the tool post grinder, regrind the taper, regrind the nose, but I think it's done now. The second time that I ground it, I went and re-watched Robin's precision spindle rebuild video, and actually retained a lot more of the information the second time around. But when I reassembled this thing the second time after fixing the lock nut, I followed all of Robin's tips. Turns out, Robin knows what he's talking about. Surprise. So, a couple of things that I did. I put the spindle in a refrigerator to cool it down and shrink it just a little bit. I put the bearings on a hot plate and warm them up a little bit. So I put the bearings in the housing, and I lubricated the whole spindle with CMD extreme pressure lube. It does a great job at preventing scoring on things like press fits and high pressure situations. Put a thin layer of that pretty evenly around the whole spindle, and then I went to very lightly press the spindle together, and I was able to do it with just a real light touch on an arbor press. Another thing that I did was polished the surface, the outside surface of the spindle, like the outer diameter that's in the bearings. I polished that with precision ground flatstones. So I put it on the lathe and ran it at, I don't know, probably 300 RPM, something like that, and just held the flatstones on there and ran them up and down the part while the lathe was running. That was another tip from Robin's video, and that actually did a great job of removing the little bit of scoring from the first time that I had assembled this without CMD extreme pressure lube. So that's a great way to recover from past sins. And I polished almost every surface that's near the bearings. I was much more careful about deburring, because Robin points out even a surface finish like this that's just kind of dull, it might have little tiny burrs, kind of little hair burrs coming off of it. Those can fall in your bearings. And when you're talking about car wheel bearings, who cares? But when you're talking about a lathe spindle that needs to be accurate to under a 10,000th for the lifetime of the spindle, and you're talking about $300 worth of bearings, those little fragments of steel matter a lot. And finally, another good tip from Robin's video is he recommends everybody take a look at the Timken spindle bearing catalog, because they've got a whole section on engineering their products in, but it's a lot of just great general tips on dealing with spindle bearings and designing spindles and that kind of thing. And that was actually where I got a lot of the information on clearances in these homemade Labyrinth seals, was from that catalog. So another great resource. You can just barely see it here, the spacer, the bearing spacer right in there. The faces of that need to be extremely parallel. That was the one part on this that I actually did properly on a surface grinder. I had a couple of friends who were friends with a professor who had a surface grinder in his lab. So we all asked very nicely, and he generously let us use his little Herrig surface grinder for a couple hours, and we knocked that out. They did great on that. I think it was parallel to under a tenth, so that went fine. As you can see, it's pretty low friction now, very low effort to spin it, and that's important on a lathe, especially when you start using a 4-jaw chuck or some other situation where you need to put an indicator on the part. I have this little baby 4-jaw chuck from Taig, and I have an arbor that I thread the chuck onto the arbor and then grip the arbor in a collet in this spindle, and it's a little wacky looking. The chuck's actually meant for the original Taig spindle. It's 3/4 16 thread, but it works fine on this spindle too. And so it was important to me to maintain that pretty low friction feel for indicating in a 4-jaw. Those of you who've ever done that before know what I'm talking about. When I initially did this, I used contacting grease seals, like just rubber lip seals, real similar to what you'd see like on a hydraulic cylinder or on any kind of rotating shaft really in industrial equipment. And those did a great job sealing, but they generated a ton of friction. And at low speeds, when you're turning it by hand, that was just annoying. And because, you know, it would turn like this far and then it would stop. You'd have to put in a bunch of effort to keep it turning. And at high speeds, it was kind of a problem. Depending on the speed, I was getting between a 10 and a 25 degree Fahrenheit temperature rise on the spindle itself here, just from the rubber seals rubbing on it. Even with a little bit of oil on there to try to make that better, it was a lot of heat being generated at, you know, 1500 RPM and over on those seals. So wasn't really comfortable with that, and I ended up designing some Labyrinth seals. Labyrinth seals. These are probably the least professional Labyrinth seals you've ever seen, but they should still be better than just a cover like you'd see on a Chinese mini lathe or something, where it's just a cover over the bearings with a couple thou of clearance or something. Alright, so I've been talking about contacting and non-contacting seals, and some of you may not be familiar with what a Labyrinth seal is. I know I wasn't until I got into this project, but this is a CAD model of the Labyrinth seals that I designed. So let's take a look at how they work. So I'm going to start with the moving part of the seal, which I'll call the rotor. This is the part that actually mounts on the spindle and spins. In my case, I have 4 set screws on this, which allow me to kind of dial it in like a 4-jaw chuck. That's not ideal, and if I had this to do over again, I might actually put an O-ring groove and have it lock onto the spindle with the friction of an O-ring, because that would probably self-center well enough, and it would just be less fiddly to deal with. But this design seems to work okay, and it's got a very, very, very small gap, and I put some grease in there anyway so that nothing can really work through the gap between this and the spindle. But this is the rotor, so it's got a little face groove in it, and when you mate it up with the stator, let's look at the stator by itself for a second. The stator has kind of a matching groove in it, and this mounts on the front of the spindle with these little holes for socket head cap screws. When you mate these two up, the two grooves kind of go together and they get very, very, very close, but they don't actually touch. And so the way that this is supposed to work, and again I say this as an unqualified electrical engineer talking about how Labyrinth seals work, so take this with a grain of salt, but the way they're supposed to work is the number of sharp turns in here make it a very, very difficult path for any contaminants to get through the seal. And so you'd almost have to have a pressurized
stream of contaminants, almost like a sandblaster or something, to be able to get past this. Your typical little stray speck of grinding dust or something floating in the air, it might get lodged in here, but it's going to hit one of these corners, and it's not really going to make it very far. That's the idea anyway. So that's the idea behind how these work. In the case of this spindle, I also added a little shim gasket thing. My original intent was to have these laser cut out of some spring steel or something like that. Let's turn off the section view so you can really see. But I 3D printed them in various thicknesses to figure out which kind of offset from the spindle housing worked the best, because that offset was what I was using to set the gap between the rotor and the stator. I was using the offset to set this gap right here and this one. So I wasn't sure exactly what number would work the best, so I just 3D printed a bunch of these shims in varying thicknesses and kind of trial and errored my way through that. And I ended up, at least for now, I'm going to stick with the 3D printed ones because I thought about that's actually going to act like a gasket to a significant extent, and it will comply with any imperfections in the spindle housing or in the face of the stator, and it'll create a seal there just like a gasket. So it's kind of serving double duty as a gasket and a shim. I'll have to be a little bit careful and make sure that that doesn't start to dissolve with any solvents that I use, but I don't use that many solvents on the lathe, and I printed them in PETG, so it should be fairly resistant to that. We'll see how these hold up. But yeah, this is how I design Labyrinth seals, and the clearance in here is 5 thousandths. I aimed for that in real life. In practice, that's a pretty tough thing to measure, but I think I got in the neighborhood, and so that should at least do a better job than just a simple cover with a straight gap at keeping contaminants out of these bearings.
But I made these a combination of on the Taig mill and on the Taig lathe with the original spindle and on the university lathe. I actually used the heck out of the Taig 3-jaw chuck to make these because it has very inexpensive soft jaws. You can buy a set of soft jaws for this thing for like $12. And so even when I was doing, there's a trepanning operation involved in these seals, and that required a bigger lathe. It required the rigidity of a bigger lathe. But even when I was doing it on the bigger lathe, I just took this, threaded the chuck on there, and gripped this in the 3-jaw of the bigger university lathe, and then machined these, took a skim cut on these soft jaws in place, and that worked awesome for keeping these big, large diameter but thin parts centered up and given plenty of registration surface on them, so they weren't wobbling like this. So, plug for the Taig 3-jaw. Honestly, if you are looking for the behavior of a normal 3-jaw chuck, this thing sucks. Aluminum isn't grippy enough. If you're expecting a normal 3-jaw on one of these lathes, you're going to be much better served by the 3-jaws from Shoreline, even though they're over twice the price. But I will never not have this in my toolbox, because when you need soft jaws, this thing is amazing. And they're cheap enough that you could probably have more than one around with different sets of soft jaws on them. I just wanted to show real quick how the bolt-on T-slots work, so to speak, and why I designed them the way I did. So they're the same profile as the T-slots everywhere else on the lathe. So like they match the T-slots here on the cross slide, which means that they take a regular 1032 square nut. So I ordered a pack of those on McMaster-Carr, and I just keep a bunch of them around, and some 1032 socket head cap screws in various sizes. I can put that in the slot, and I can fixture something on top of here if I wanted to. Doing it this way did a bunch of things. one, it leaves the door open for me to fixture like some kind of indexing setup with like a dividing wheel and a pin or something on the back using the T-slots or any other kind of weird extra feature. Two, it lets me attach magnetic bases like this so that I can use indicators on my parts without putting this enormous mag base on the bed of my tiny lathe. And three, it let me manufacture the T-slots like this without having to use a T-slot cutter. So I actually did most of this on the little tiny Taig mill over here, which probably wouldn't have been able to tolerate big T-slot cutter kind of taking all, like a key seat cutter, taking all of this in one bite. I'm sure I could have done that like on a Bridgeport or something, but I don't think it would have worked very well on this little mill. But doing it this way let me just work my way down with an end mill and then bolt these on top. And sure, it took a little longer, but I do this as a hobby, not as a job, so I don't really care. So I'm actually pretty proud of how that came out, because it solved a number of problems, and once I polish the top of this a little better, it's going to look pretty cool too. So I've got a piece of roughly 5/8 inch bar. It's about 5/8. So we're going to put it in a collet and try some cuts. This is 12L14, by the way. Spindle wrench that I had lasered or water jetted or whatever was done to it. I didn't make it. And an ER32 wrench. I'm just going to touch off here and kind of clean up this surface so we've got a good reference to work on. Okay, so I'm going to try just some plain turning first. So we'll go 25 thousandths. Again, this is 12L14, and this is just like a no-name Amazon carbide insert. And it doesn't seem to mind that at all. Okay, so that was 25 thou. And we'll go ahead and go 50 thousandths. And I haven't trimmed I haven't set the give on the carriage in a while, so I'm going to tighten the carriage lock just a little bit to kind of preload that. All right. So it's taken that really, really well. Honestly, I'm not sure I trust this insert beyond 50 thou. So let's try something different. Let's try parting. Parting is something that the Taig Lathe has never been any good at. Everybody that owns one knows that. People have come up with all kinds of innovative parting tool designs and spring-loaded holders to reduce chatter and all kinds of clever things. I have a pretty standard rigid holder, and I believe that's a 1/16 parting tool. Pretty thin. It is high-speed steel, not carbide, so I'm going to slow this thing way down. We're running about 125 RPM. And in this case, I am going to put just a little bit of tap magic. And I'm going to lock the carriage. seems to be handling that great. I'm gonna go ahead and bump this up to a little faster. And it's really still handling it great. Alright. Let's see how good my center height is. If I get a little nub in here at the center. I'm gonna speed this up a little more now that we're closer to the center. We got a little nub on that part, but this part's actually almost smooth, so center height on the parting tool is pretty good. And that's a pretty respectable finish. Look a lot more respectable if I could get the camera to focus on it. There we go. Pretty respectable finish for a lathe that weighs under 100 pounds. Okay, so I've got my indicator set up on here. This indicator reads in 10,000ths of an inch. One tick mark is 1/10,000th of an inch. So I'm going to use the fine adjust on the little Noga arm and get it zeroed out as best I can. And then we'll kick the lathe over. So it looks like maybe there's a little ding or a little chip or piece of crud in there. But other than that, there is under 1/10,000th of runout on this thing, which is incredible. I'm blown away that it worked out that well. Let's try the spindle face. How good is that? Yep, same thing. Under a 10,000th of runout on the spindle face, which really for normal collet operation, this face shouldn't matter. I just went ahead and ground it while I had it set up in case I made some other kind of tooling that threaded on here and needed that face to be reliable. So I've still got a little bit left to do on this. I gotta do some final machining on this top surface on my little bolted together T-slots. They work well, they just haven't been machined in place yet, and I'm gonna do that and then probably polish them just to make them look good. And then I think I'm gonna order an actual metal tag for this somewhere down the road. And I probably need to make a cover for the rear of this so I don't have this exposed pulley while the lathe is running, because I know my own tendency while using the lathe to set my hand here and catch it in the pulley. It's probably not a great idea, but the core of the spindle, all the actual finicky precision work is pretty much done. I might also add a place to put an indicator arm or a carriage stop down here, similar to what's on the original Taig spindle, because that's pretty nice. But yeah, would I do this again? Probably, but I won't choose to make another one. I now understand why, especially if you factor in buying all this material. A lot of this material was salvaged, particularly the giant chunk of aluminum rescued from a scrap bin. But if I'd had to buy all of this material and I actually mathed out my time, it probably would have been 10 times cheaper for me to just spend the $600 on the spindle from Taig. And that's not an endorsement of that spindle. I've never even used it. I don't have any kind of relationship with Taig other than being a customer. But if you're thinking you're going to build your own spindle to save money, you're probably not. If you're thinking you're going to build your own spindle to prove to yourself that you can do it, and as a fantastic learning experience to understand how spindles are built, absolutely. This was definitely those things for me. So, comment if you have any questions. Hope that was interesting. Thanks for watching.
If you made it this far nonstop, you really need help, because that's a lot of stuff to sit through.